All right, these notes are going to go into your AP Bio Lab notebook. So this is the bound composition notebook, not the spiral notebook. So chances are you've done plenty of graphing in your science career up till now, and so we are going to add to that. We are going to use the graphs that you've done before in different ways, and so it would be a really good idea to have a spot or resource to kind of summarize different types of graphs and what you might use those graphs for and what they can be helpful with. So a line graph, generally it's going to show a change over time. So whenever we think of a line graph, you usually show how fast something's going or how volume changes over time. But one of the more accurate, I don't know if accurate is the right term, another way to describe a line graph is when you compare two infinite variables. So for example, time is an infinite variable. You have 1 minute and 2 minutes, but in between 1 minute and 2 minutes, you have seconds and milliseconds. I mean, you can divide it down as much as you want. So that's why time is an infinite variable. Volume is also an infinite variable. You have 1 liter and 2 liters, but you can divide them into milliliters, and you can divide those into microliters. You can divide it as much as you want. So volume is also an infinite variable. So a line graph is typically used whenever you compare two infinite variables. So how does volume change over time? Both volume and time are infinite variables, so you can use a line graph to show that. A bar graph is going to be used to compare separate but related data. In a typical bar graph, in just a plain old bar graph, the bars are separate from each other. They have the same amount of space between them because they are comparing separate but related data. A histogram has bars that touch because it is a continuous set of data that shows distribution. A histogram is a continuous set of data that shows distribution. Standard curve, that's probably a new one for you. Standard curve is a line graph with a line of best fit used to determine an unknown by comparing to known data. Standard curve is a line graph with a line of best fit used to determine an unknown by comparing to known data. Standard error. You use a standard error graph to draw conclusions about data. You can infer if data sets/groups show a statistically significant difference or if the differences in data are just due to chance. So standard error graph is used to draw conclusions about data. You can infer if data sets/groups show a statistically significant difference or if the differences in data are just due to chance. Then finally, box and whisker. Box and whisker plots are used to compare sets of data and show distribution. Box and whisker plots are used to compare sets of data and show distribution. All right, so you are going to have a worksheet that looks like this, but we are going to add information to your worksheet before you put it into your comp book. However, once that information is added, you're going to lay the worksheet sideways, and you're going to put 2 little pieces of tape on the top, 2 little pieces of tape on top on the other side, and then you're going to fold it in. And that way, it will go right in between our graphing vocab, and then we'll add this information here in just a second, but all of this is related to it. So that's going to keep it in a nice, convenient spot. All right, this graphing resource sheet should be helpful for you to make sure that you get everything that you need on your graph. AP Bio testing, sometimes they have you create a graph, and so it should be really easy points on that test. The problem is that we have a tendency to leave things off of our graph, and so it's really easy to miss those points. So starting with a line graph, let's just wait right here. All right, so identify the variables in your experiment. The independent variable should be labeled on the x-axis, the horizontal axis. The dependent variable should be labeled on the y-axis. So remember, the independent variable is also known as the manipulated variable. Dependent variable is also called the responding variable. So one way that you can help remember what goes where is dry mix. So on your graph, dry mix. Dependent, responding goes on the y-axis. Manipulated, independent goes on the x-axis. So even if you don't remember the responding and manipulated part, if you remember dry mix, dependent goes here, independent goes here, and that should help. So I have plotted some points on here, and I have drawn a line in between those points and not connected them. You've done plenty of line graphs where you connect the points, and in AP Biology, there will be times where you connect the points with a line. A lot of times, however, we have data that we need to use a line of best fit for. The line of best fit shows the general overall trend in the data, and it does not connect the dots, because connecting the dots probably wouldn't make a whole lot of sense. So we would just have a big squiggle. But this way we can see generally as we increase this variable decreases, it's going down. So that line of best fit, that trend line, gives us a general idea of what's happening on the graph. Some of the things that you need to remember when you are labeling your graph is that you need to make sure that whenever you number your graph, that your scale that you choose fits the range of your data. Your numbering needs to be consistent. So if you want to count by ones and you can fit it on there, that's great, go for it. But if you start counting by ones, you have to count by ones all the way up. Your x-axis doesn't have to have the same scale. So if I count by ones on the y's, I can count by fives on the x-axis. That's fine. It just needs to be consistent across the axis. You want to spread out the graph as much as possible on the grid that you're given. So you don't want to have everything in one little corner or one little spot, because then it makes it very hard to read and analyze the data. So even though I can fit from 1 to 10 right here, maybe I want to spread it out 1 to 10 here, and I can fit 1 to 10 here, but I want to spread it out. So that way I can see that data and I can get a good idea about what the trend is on the graph instead of squishing it into one little spot. Spread it out on the page, on the grid. I don't like the word page because you have to make sure that everything stays on the grid. You can't take your grid graph and then draw in extra lines above or beyond. You can't do that. Everything has to be on the grid, on the graph that's provided to you. So do not extend above or beyond on the piece of paper. Make sure it fits the graph. Number and label each axis. You need to make sure that you label each axis. We need to know what those numbers are. Plot data points with dots for a line graph or a scatter point graph. If you're using a bar graph, obviously we're going to put bars on there, but most of this is generally speaking for line graphs. Plot the graph. Provide a key if necessary. Title the graph. Title would be a very good thing. And you can just say versus, so volume over time, or volume versus time versus volume. That's fine as well. But ideally, think of it kind of like a title of a book so that you're sort of telling whoever's looking at that graph what's going on there. A lot of times, people that are looking at graphs have not done the experiment, so they have no idea what that data means. So give them a title that's going to tell them what's going on. All right, one of the things that I want to talk about really quick is you have to watch for the correct amount of space between your numbers. So if I put a 0 here, and I put 0.5 here, and then 1, and then 1.5, I have to make sure that I have the same amount of spaces in between each one. So here's 0, 1, 2, 3, 4, 0.5, 1, 2, 3, 4, 1, 1, 2, 3, 4, 1.5. That makes sense. That works. But I cannot say, hang on just a sec. I had to erase a little bit there. So I can't say, if this is 0, I can't all of a sudden make this 0.25 because 0.5 is right here. So 0.25 is halfway between 0 and 0.5. And so if I have 1, 2, 3, 4, 5 boxes, it needs to be 1, 2, 0.25 needs to be about right here, not right there. So you have to watch that because sometimes we do have a problem with that. We do have a problem with making sure that we have the same amount of space in between each one of our values. If you have different amounts of space between them, then it's going to skew your data. It's going to make your data messed up. All right, so on the back side of the graphing resource sheet, we have a couple of example graphs. And so for this one right here, that's a great start. We have labels down here and we have numbers. However, we still have no idea what these mean. So besides labeling each one of these bars, we also need a label as to what do these letters stand for. So let's say this is first hour grades. Now I know what those letters stand for. Same thing for these numbers. What do the numbers mean? You still need to go ahead and label that. Number of students, although I would recommend that you turn your notebook sideways to make it easier for you to write. Number of students. Ideally, we want to have a title on here. You can have number of students per grade or grades for first hour students, and that's fine. So we've got a nice descriptive title. We have numbering that's consistent all the way up. We have a label to tell what those numbers mean. We have labeling that's consistent all the way across, and we have a label that tells what those letters mean. Our bars are the same width and have the same amount of space between them. For the love of Pete, I don't understand why people don't use the grid. We want to make this nice and neat. We want to make sure that the bars are the same size because different size bars mean different things. So use the grid. Make sure that if you want your bar to be one box wide, then they're all one box wide. They also need to have the same amount of space between them, and technically there's the same amount of space here because this would be D and nobody has D's, so I have it shown, but that would represent 0 right here. So I still have one space in between each one of those bars as well. Make sure that you watch for this. So this is your typical bar graph that is comparing separate but related information. Separate because each grade is separate, but it's related because it's all the first hour grades. All right, so this second graph is still a bar graph showing separate but related information. But now this is first hour grades of 2018. Now I have 2 bars. So you need to make sure that you have some sort of key that is showing what do those bars represent. So if I have this color, this represents first semester. And then if I have this color, there's the color, that represents second semester. But it's giving information on what those bars mean. So it's still the same class period, it's still the same year, but now I'm comparing within that year how many A's first semester, second semester within that class. So it's still comparing separate but related information. Title, once again, would be nice on here. We've got labels that say what the numbers and letters stand for. All right, so now we have a histogram, and so these bars are touching because it's showing a continuous set of data. Number of caterpillars, we have consistent numbering. We fit all of the numbering on our graph. Length, and any time that you have some sort of measurement, length, volume, time, if it needs a measurement, then it needs to have a metric unit. You must have metric units on your graph. So title would also be nice on this one, but this is our histogram. So the bars are touching, it's showing a set of related data, showing the distribution of a continuous set of data. All right, some other tips and pieces of information. First of all, do not extend your data outside a given grid. Renumber your axis to fit the data. All right, so what does that mean? That means if this is the grid, I have to fit it on this grid. I cannot, and find out my data goes above it, I can't go ahead and draw in lines over here so that I can fit my data. It has to fit on the graphing grid. So if it doesn't, if something happens, then go back and renumber your y-axis so that it fits on there. All right, so a lot of people like to use this little squiggle to show the break in data. So this little squiggle line this little squiggle line shows a break or a gap in the data, but you can only use it if all of your data is still included. So if this is my data, here's my height data, and here's my diameter data. Well, my diameter doesn't start until 20 millimeters. So I don't want to count 0, 1, 2, 3, 4, 5, 6 because I'm not going to fit it on there. So I put the little squiggle there because I'm starting at 20, and it shows that this amount of space right here, these two boxes, should be only equal to 10. Should be equal to 10 millimeters because this is 5 and this is 10. So this should be 5, 10, 15, 20. But because of the fact that I have so much space on my graph and I need to conserve space, put this little squiggle in there to show that I'm going from 0 to 20 and that these two boxes right here aren't showing an accurate distance in between my diameter values. So I'm starting at 20, and here it's consistent all the way up. Every one box is worth 5 millimeters. Your numbering has to be consistent. The only reason I can do that is because there's no data below 20. If I had, let's say, 15 here, somewhere on here, if the height at 1 centimeter is 15 millimeters, then I can't do that. I have to be able to fit all of my data on the graph and have a consistent counting and a consistent spacing. Scatter point graphs. Scatter point graphs need a line of best fit, need a trend line. So scatter point tends to be a lot of data that's spread out a little bit more, and when you put your trend line in, you want to try to have as many points above the line as below the line, as best as you can possibly do that. Once again, remember, whenever you have measurements, you must have metric units on your graph. And then we're going to look at standard error graphs here in just a minute, but let's go ahead and fit this in here where we have room. Standard error, SE graphs, standard error graphs can be bar or line graphs. So the ones that we're going to look at here in just a moment are going to be bar graphs that have standard error bars on it. These little I-beams are standard error bars. But you can also see a line graph that is a standard error graph, so don't be surprised by that. Next, we are adding information to this worksheet. So you're going to pick up this worksheet, and so we're going to add a little bit of information to the front and back of that. But again, we're going to tape it in the same way as our graphing resource. I'm going to turn it sideways, a couple little pieces of tape on the top, a couple little pieces of tape on the top on the opposite side here so that we can tape it in. All right, so you need to go back to the PowerPoint about standard deviation and standard error and kind of look at what standard deviation means and what standard error means. It's a very short PowerPoint, but it's somewhat helpful. We don't worry a lot about standard deviation. Standard deviation is essentially how spread out the data is. What we analyze is we analyze using standard error, but standard error comes from standard deviation. So this is hopefully giving you a little bit of a visual as to where that information comes from and how we get those bars. All right, so I have these two sets of data, and it looks like it's exactly the same set of data, except for we're looking at maybe more individuals over here. On graphs, you always have to pay attention to the variables, always, because that's one way that people can manipulate data. So if I look at the counts over here, the count on the top one is 0, 5, 10, 15, 20, and the count on the bottom is 0, 2, 4, 6, 8. It's counting by twos, so that doesn't mean that there's more data here. That just means that the data on this one is more consolidated toward the mean. This first graph has a standard has a mean, 40, 50, 50, has a mean in the same spot, but does not have quite as much of a standard deviation. It's not spread out as much because all of that data that's down here is compacted into this smaller amount of space. There's a different spacing between the two of them. Standard error is the accuracy of an estimate, the accuracy of the mean. So when we look at sets of data and we see that the mean is 50 kilograms, how accurate is that in a population? For this one, the standard error is much more accurate. We can be much more confident saying that if you pick up another random individual from this population, it's going to be pretty close to 50 kilograms because there isn't a whole lot of deviation from that mean. In this one, there is a ton of deviation from the mean. So even though the average, the mean is exactly the same as graph A, don't have a whole lot of confidence at all of the fact that I'm going to pick up another individual from this population and it's going to be close to 50 kilograms. There is too much of a chance for it to be anything other than 50 kilograms. Whenever you are graphing these with standard error bars, it's probably going to look a little bit something like this. So A, here's my average. B, here's my average. The mean is the same for both. And so my bar is the same for both of these because the bar represents the mean, represents the average. So this would represent 50 kilograms, this would represent 50 kilograms. But the standard error bar, the standard error I-beam that we put on here shows how confident I can be that this is close to the mean or this is accurate according to the mean. So on this one, we don't have a lot of deviation. Our standard error bar is much smaller. This one, we have a lot of deviation, so we have a very big standard error bar. We can't be confident in the mean. We can't be confident that we're going to pick up another individual and it's going to be really close to 50 kilograms. So a smaller standard error means that we're going to be a little bit more precise. Standard error tells how far your sample mean deviates from the actual population. We want big population sizes so we can get a lot of data. Okay, so here's another two graphs, graph C and graph D, and once again the counts are different on here, so it looks like there's a lot of data here and not a lot of data there, but it could be skewed because of the fact that they're not using the same values, which you probably should do. So when I look at these guys right here, the mean is once again still exactly the same, but now because I don't have a lot of data to draw from, my standard error is a lot less precise. I have more standard error. I'm not very confident at all that when I pull an individual out of this population that it's going to be close to 50 kilograms. I just don't have enough individuals to find out if that mean is a really solid mean. On this one, I can be pretty confident. I have lots of data in here, which is going to help me decide that yes, this average is a pretty good average for this population. So these standard error bars, because of the fact that I don't have a lot of data to analyze, I'm going to have a big standard error. Because I have more data, I'm going to have a smaller standard error. All right, so how can we utilize standard error in our analysis of data? So here's the front side of that worksheet. And let's say that these graphs represent, we're using two types of fertilizers, and then we're looking at height. So types of fertilizer A and B, height in centimeters. So we go ahead and plot our graphs, we create our graphs. The bar represents whatever the mean is of that set of data. So the mean height of A, mean height of B. The standard error bars are what we look at to analyze to see, is there really a statistically significant difference? So when I look at this graph, let's say I didn't have these I-beams on here. It looks like fertilizer brand A grows plants higher than fertilizer brand B. So yay, buy fertilizer brand A, right? So companies can use this to manipulate their customers and get them to buy. But if we actually analyze this data and we find out that our standard error bars have a lot of overlap, that tells us that even though there's a difference in height from A for B, that it is not statistically significant. So that's like the 51-49. I mean, that's close enough to being 50-50. It's close enough to being the same. Because there's overlap here, A really isn't statistically significant in its amount of data showing that it's going to grow taller plants. Less overlap means that where our differences are probably getting to be more statistically significant. But if there's overlap on it, that's probably not going to be statistically significant overall. When we get to the point to where we have our bars, and so this is average of A, average of B. Now the height is definitely more in A than B, but then after we put our standard error bars on here, we see that there's no overlap. That's telling us that that difference is statistically significant. And I can be confident that fertilizer brand A is producing taller plants than fertilizer brand B. The thing about science is that even though this is showing that there is a statistically significant difference, we can never be for sure. We just need to test more. All right, so we're going to take a Post-it and on top of this one. So even though fertilizer brand A averaged taller plants, the difference is not statistically significant because of the overlap in the standard error bars. And on this one, fertilizer brand A most likely had an effect, but we need more analysis because we can never be sure in science. So we always want to do some more analysis.